Hello, everybody. Good morning, good evening, good afternoon, wherever. So welcome to this session at ADAS. So the first invited speaker is Matthew Graham, well known to this community. Matthew is a professor of astronomy at Caltech and also the project scientist of the Zwicky Transient Facility, and he's going to speak about the lessons learned from their first 300 million alerts. So Matthew, the floor is yours.
Thank you, Christoph. Thank you very much for the organizers for inviting me. I would hopefully have been in Granada today, but obviously I'm not. In spite of my background, I'm actually still in Pasadena. So I want to take you back about 12 years to ADAS 18 in Quebec, about this time of year, where I gave an invited talk, the last invited talk I've given at an ADAS, on what astronomy in 2020 would look like. And there were a number of predictions I made in that particular talk, and you can go and look at your ADAS proceedings from then. Back in 2008, we said that LSST would be operational in 2014, so we would now be in year 6 of LSST. LSST would require one of the top 1,000 computers in the world. SKA would have been coming online this year, and it would have required the top computer in the world. And I predicted that we would wake up every morning, and instead of astronomy picture of the day, we would be looking at the universe today, which would be a morning digest summarizing changes in the position, the flux, the spectra, etc., of billions of objects that we were monitoring in multi-wavelengths across from the local solar system out to the most distant galaxies. And so you'd get a daily summary or a morning summary of the things that had changed in the universe while you've been asleep, and so you could figure out what was interesting. We were expecting that we would be dealing with petascale or maybe even exascale alert streams, and that we would require web scale computing resources just to process this torrent of data. We had these notions that, however, that disparate set of events could be linked together in some way with archival or supplementary data in a machine comprehensible way, that we would have representations that both the human could read and the machine could process. And we thought that the way forward was with linked data, with RDFA, with the semantic web. We also thought that actually much of the data mining and analysis with these large alert streams would be performed by intelligent agent avatars that would be existing out there in the cyberspace somewhere, and that we would not be doing a lot of the processing ourselves. We would be just looking at the results and making the policy decisions or figuring out what was interesting. We noted that there would be a problem of merged clouds, hypervisors, the buzzword of 2008. We were concerned that these cloud environments, the different cloud environments, how would I integrate across all of those providers who are making this sort of web scale processing available? We identified that to handle this, we would have to be doing declarative parallelized programming in a language called Curry. I think that has completely died the death. I haven't heard of Curry since. I mentioned in my talk 12 years ago. We also predicted that the bulk of astronomical data would no longer be in relational database systems, but in NoSQL or key values pairs or something like that. And I ended my talk and the subsequent publication by saying that I would be prepared to come back in 12 or 13 years' time and give Astronomy 2020 reflections on where I went wrong. Well, here I am now. And so this talk is actually sort of building on where we were there with that mindset, and where we are with the state of the art. We don't have LSST yet. We don't have SKA yet. What we do have in 2020 is ZTF, the Zwicky Transient Facility, for which I am the project scientist. And let me give you a very quick overview for those who are unfamiliar with this. This is a survey that's been running for 3 years, and we've just had our renewal of a further 3 years. We use the 48-inch Schmidt telescope at Palomar Observatory, which is the telescope that was used back in the 50s for the original POS survey on photographic plates, but we've replaced the photographic plates with a large CCD detector, 16 CCDs, 47 square degree field of view. With a 30-second exposure, we can survey about 4,000 square degrees an hour. As I said, we're normally 6 years. We've just finished our first 3 years. We're moving now to, because the way that the project is funded, we spend half of our time on public surveys, which is now a 2-night cadence of the northern sky visible from Palomar Observatory in GNR. And then 30% goes towards the ZTF partnership and 20% is for Caltech programs. The partnership and Caltech also have an I-band filter that they can use. I say nominal exposure time is about 30 seconds. That gets you to a 20.5 depth. We have about 2 arcsecond image quality. And whole northern sky from deck of -30 above. We send out real-time alert streams, which is one of the big things that ZTF has done for the community in preparation for LSST. We send out several 100,000 alerts per night of things that have changed in the thousands of square degrees that we survey every night. VO event, which was the old IVOA alert format, was not sufficient for the data that we wanted to pack into an alert structure. And so whereas Catalina Sky Survey that I've previously worked on sent out a small number of VO events a night, for the industrial scale alert stream that we wanted going forward with ZTF, we came up with an Avro-based packet. So Avro is an industry standard for messaging. And most importantly, it can contain binary structures. And the binary structures that we wanted to put into the alert packet was the thumbnails showing the new image, the reference image, or the template in LSST parlance, and the subtraction between the two, which shows you what the transient is. We have unique spatially matched alert names, which have these sort of 7-character alphabetic strings. We also include a 30-day rolling window light curve history. So there's a 30-day photometric history of that particular transient from ZTF data. We include then a whole load of other metadata in our alert packets. The alert packets are typically about 80 kilobytes in size, 85 kilobytes in size. Some of those additional data is the real bogus score. So we have certain machine learning classifiers which run over our data and give you information: distance to the nearest pan-star sources, distance to the nearest solar system object, some degree of alert history, that sort of thing. So that's the alert packet. That's the infrastructure we've built up, which is sort of similar to some of the stuff we thought about back in 2008, I guess. We've fostered an alert brokering ecosystem, trying to get the community ready for LSST and other projects. So we've encouraged those who want to be LSST brokers to sign MOUs with ZTF, and so that they can get the infrastructure in place for filtering, get community users in, start making their own discoveries. There's the LSST broker in Chile, LASER at Royal Observatory Edinburgh, Fink in France, Antares from Noir Lab here in the US. LCO has a simpler one, and one of our newest ones is the multi-messenger astrophysics initiative that's being led from NCSA. They're all serving these to some degree of the community, providing slightly different flavors of filtering, slightly different flavors of classification, and getting ready very much for LSST. So this is a good thing that ZTF has provided, and one of the things that's a very good success, we think, for our survey. So ZTF 1 officially ended on September 30th this year. It ran for 929 nights. Data was taken on 734 nights. A total of 480,000 exposures overall. 22 million square degrees of sky was surveyed. That's equivalent to what LSST will do in its 10 years. As I say, we've got a larger field of view. So in terms of just 2D sky coverage, we've now surveyed the same amount of sky that LSST would do in its 10-year run. Out of that, we've produced 300 million alerts. About 100 million of those come from the public data stream. More come from the private data streams because we have higher cadence observations. About 6.5 million of those associated with known solar system objects. We've done 3 data releases to date. The next one's coming in December. That's 5.6 billion sources with light curves in GRI. We ourselves, the project, have produced over 90 publications, and there are lots of publications now coming as the community catches up and starts trawling through our data archives, through the alert archives, as well as the real-time stuff. In terms of the science that we've generated, 5,000 supernovae, I think at least half of the supernovae detected now are and reported to TNS are coming from ZTF. Tidal disruption events, changing look quasars, neutrinos from tidal disruption events associated with our detections, ultra compact double degenerate binaries in the galactic plane that will act as LISA sources, asteroids, comets, asteroids within the orbit of the Earth, asteroids within the orbit of Venus, but no Planet 9. Lots of LIGO follow-up, but no neutron star, or black hole, neutron star EM counterparts, but possibly a black hole counterpart. So as you would expect for any modern sky survey, generating lots of science, LSST will do even more, et cetera, et cetera. Some of the problems we've faced is it turns out that we've probably been the most complex time domain survey ever scheduled, not because it's not just a case of us doing that nightly or bi-nightly, tri-nightly scanning of the galactic plane and the northern sky, because of the way that we are this 40%, 20% funding and broken up. Each of those has their own separate servers that they want to put in, and trying to put those all together has been a real challenge. And Eric Bellum at University of Washington has developed a scheduler that's been very effective on this. Almost 90 survey configurations, filter exchanges, target for opportunity events, all that sort of thing, a real success. But one of the things that you might not have thought of for just a simple sky survey. We're not actually a simple sky survey, we're quite a complicated sky survey in those sort of things. So going back to those original ideas we had in 2008, how do those factor, or how do those join up with some of the things we're seeing? So this whole idea of, the fire hose is the thing to be worried about, the data volumes, etc., it's completely not true. We have the technology. ZTF is a 10% LSST according to a number of metrics, including data volume, data processing. We can easily scale up by a factor of 10 to get there with what we have in terms of infrastructure, in terms of computing. So we have the technology to handle the volume and such. So that's definitely not an issue. And we're very clear on that, I think, now. One of the things that we've noticed, however, is that even within the ZTF partnership, there is an effort to reinvent the wheel many times. Individuals, groups attempting to solve the same problem. I think we see that as well in the brokering communities. We have 15 to 20 brokers vying to be LSST brokers. They're all facing the same sort of problems, and a lot of them are working within their defined funding communities, which is to be expected. But it means that with finite resources, trying to tackle the same problem, we're maybe falling short of areas where we should be addressing things. And I think that's certainly one of the things that we've seen from ZTF, as I say, both within our own project and also in the broader community of people who are trying to use ZTF alerts and that sort of thing. So that's one of the things that we really should work as a community to get around. There's this whole idea of, as I said, back in 2008, we thought we'd all have intelligent agent systems working on this. So we'd have machine learning plus the right sort of training data sets, and then humans in the loop to do the labeling, but we could take those out. The problem is we haven't taken the humans in the loop out yet. And that introduces latency, inefficiency, and non-repeatability into a lot of the things that we want to have, where we want the machine learning actually to be doing a lot. We still have people who are doing daily scanning of alert streams when we should believe the rule sets or the AI systems that we've trained to be able to identify the things that are in string and just leave those to put that in. So we don't have enough confidence yet in our machine learning to move fully into the AI in the loop. And you would have thought that we would have been there. I think, in 2008, we would have thought that in 12 years' time, we would have a much stronger reliance on machine learning and AI, particularly with the rise of deep learning in the last 5 years, than is necessarily the case in what we're seeing now. We're finding also that the history is important, that in the alert streams itself, that alert structure, you don't just want to know what has changed, but you want to know what is the history over the last 30 days or the aggregate history since the beginning of the survey of what I'm looking at. And so what we're finding is that our data archives are actually getting hit by millions of queries a day, both by ourselves and by communities, for data to say, okay, this changed last night, but what was it doing a week ago, a month ago, a year ago? The other thing is that those alerts only give you a 5 sigma change because it's coming from difference imaging. And there's a lot of the sky which is changing on slower, lower sigma variability that you're not getting in the alert stream, that you only detect when you get one of the data releases and do an archival trawl back through the history to see what has changed. And that's important for a lot of phenomena. There's a lot of slow phenomena out there that 5 sigma is not going to get you. And that's also going to be a problem for LSST. And you know, you see, I think we're going to see the buildup of large sentinel or large watch lists for doing photometric monitoring for variable sources rather than just the supernova or the tidal disruption events or the solar system objects. And this is important. The history is also important for the rates of particular transients. One of the other things we're seeing is that we originally had this idea that there would be different components in that brokering infrastructure and how the time domain infrastructure would work with marshals, with brokers, with repositories, with the TOMs that are coming online now to manage the follow-up observations. And what we're beginning to see, I think, is a lot of those are all being folded into single data management systems that various groups are putting together. So we're seeing sort of one-stop shopping, or we're seeing super apps or something like that. Even within ZTF, we have a new sort of super marshal called Fritz, developed by Dmitry Duev and Josh Bloom at Berkeley, which is integrating a lot of this infrastructure together. So it has a very powerful data management backend with all the archives there, but also allows you to do filtering of event streams. It allows you to do searches. It allows you to trigger stuff off the telescopes and whatever. And I think that's maybe something which is a little surprising. We thought we would see a more decentralized network, and that's not what we're seeing. It seems to be that people want a one-stop shop for managing the alert streams in the community usage. However, I think that the model we presented back in 2008 and the model that has driven a lot of the development of what's going on in the community has some misconceptions or some misperceptions. As I say, there's this idea that, you know, back in 2008, we were saying you will need one of the top 1,000 computers to manage LSST. You will need the top computer to manage SKA event streams. This idea of having these super cloud resources available to you is sort of quite clearly wrong. Networking, that I need to be connected to the fire hose. I need to be receiving millions of alerts a night directly. This idea that I need to persist everything locally, because I can't trust community stores or data stores out in the archives, I need to have my own local copy, and everything I receive, I need to persist. And the danger here is that we're going towards these ideas of the super app then becomes a monolithic thing, which controls everything, becomes more complicated, and then we are bound into those systems as we go forward. But I think what we're also seeing is we're seeing an evolving landscape. Back in 2008, we had this idea of working with alerts. The alert landscape should be broker-based, and that was to manage the volume and velocity of alert data. But we don't need those systems. And we're now seeing a transitioning to more general systems in the community that are not just working with alerts from transients, but are working with variable sources, that this is becoming a more general time domain environment. And we've got new use cases coming that people want to be working with the alert, but they also want to be able to handle the light curve, the SED, all as primary data objects rather than ancillary data objects that are done downstream processing. Veracity is also becoming increasingly important. I'd like to know what the provenance of what I'm doing, the provenance of the data I'm receiving, what has been worked on it already, that sort of thing. So I think what we're seeing is a transition now from from data management systems with the alert streams actually into information management systems, where we're trying to put this all together and combine it. And I think that's a slightly different landscape from what we were looking at. I think one of the ways we can make some great inroads into that is actually to decentralize and look to the Internet of Things. So this is your smartphone, your smart fridge, your smart microwave, your Alexa system at home. And one way that you can do it is the artificial intelligence systems that are making use of that are looking at hardware accelerators for doing inferencing. And this is the so-called edge TPUs. And we can demonstrate that on a simple USB plug into a Raspberry Pi, you can process a night's worth of ZTF alerts in 5 minutes or less than 3 minutes this year. So if you're looking to do really fast AI inferencing, which is probably what you need to do a lot of the classification, the characterization that you're interested in working with these data portfolios, you can do this much more efficiently on these very lightweight, low-cost systems that are improving month by month. Just last month, Coral have introduced a new dual TPU board, which gives 8 TOPS as the processing speed, which is slightly bigger than a US quarter. So we can have these systems for low cost, which could handle a lot of the computing, and with smart networking and such, we can sort of do it. The other thing that this sort of model allows you to do is actually federated learning, where you bring the model to the data rather than the data to the model. So in training these sorts of things, I don't need to have a big GPU cluster. I can do it on the edge, and I can make use of local data, local heterogeneous data, which maintains data privacy. So it maintains access to proprietary data, if that helps. And the only thing that is then exchanged with the central server is the weight of the updated model. So all specific local learning contributes to global learning. So you've decentralized the learning of your AI systems as well. And I think that's where we need to be thinking and heading towards. So a vision for 2030, I think in comparison to where we were thinking about in 2008 with this environment of data streams and such from sky surveys, it's no longer about volume, velocity, and variety of data, but it's actually it's going to be about information and knowledge management. And I think we're not going to be working with static classifications, static quantities. With the rise of even more AI systems coming through and more astrostatistics coming through, I think we're going to be having a much more fluid environment where we're going to be working with dynamic probabilistic quantities, where veracity is actually going to be extremely important, because you're going to want to know exactly what version of what produced the thing that you're looking at in terms of doing your inferencing, and what are your priors and where are they coming from. Centralized systems in that sort of environment are cost and energy inefficient rather. And I think that energy inefficiency is going to come up as well. To train these big data, these big AI models is very costly in terms of energy. So I think in 2030, we're going to be looking at decentralized intelligence networks running on these low cost components, employing commodity hardware accelerators and reusable models, where you can just use transfer learning on the edge to improve, and you get response time and save bandwidth. And so I look forward to giving a talk at ADAS 40, where I can reflect on the predictions I've made today and the environment we're looking at and see where I got wrong. So thank you very much.
Many thanks, Matthew. So yeah, let's see. So for sure, we will all want to hear again in 12 years' time or in 10 years' time. So there are a couple of questions in the Q&A, and one also in Discord. So the first one on the Q&A is, what does ZTF report to TNS?
So ZTF has, there is an automated system. So there are 2 reportings going on to TNS. The LSST broker, which is an external entity to ZTF, reports supernova, early time detections of supernova based on single alerts to TNS. ZTF project itself, we have the Ampel broker from the DESI group in Germany, which has a number of automated filters on the alert stream, and high probability candidates for supernova in both TDEs are reported that way automatically into TNS.
Okay. There is another question from Thomas in Discord, which says, you said that we do not have enough confidence in machine learning yet. So what is your opinion on why that is?
I think the problem is that we are still, scientifically, we're still very much in the mindset that everyone's looking for the rare objects. And so therefore, we're doing individual object studies. We're in an industrial alert scale mode, and we're going to be even more so with LSST. And I think somewhat conceptually, we haven't made that transition yet, where we can be very systematic and look at populations of rare objects. And, you know, if you've got 1 billion sources, that's going to give you 1,000 1 in a million detections. And we're all still looking for the low-hanging fruit, but I think we need to move into this idea that the outlier detections, the anomaly detection systems are good enough to find those rare things. And you can demonstrate that through, you know, take a training set and build one and see what you would find if you went through it and see what the system will find. And I can tell you that the AI systems do better, but there's a lack of trust in it for some reason. There's still this big scare that we're going to miss something, or that we're going to turn some follow-up facility onto something that turns out not to be real. But I think, you know, our false positive rates are such that that's very unlikely to happen and going to improve even as we go further. So I think there's a scientific change that has to happen, that we should trust these things, and we should be happy that these things are looking at the data and trusted, rather than, you know, you need nightly or daily grad students to review thousands of alerts looking for supernovae or something like that.
Okay. And what do you think will be the trigger that will bring that change?
Hello.
I think it has to be. LSST turning on. I think once you start getting, you know, 10 to 40 million alerts a night, what we've seen in ZTF, there has been, for example, in the solar system group, they were quite happily scanning very many thousands of alerts every morning looking for moving objects. Then we brought in a new machine learning algorithm, which reduced that down to a few tens every morning. And so people now trust that the deep streak system does a very good job in classification. I think when you're dealing with, you know, having to look through 100,000 alerts every day to find a supernova, you're not going to do that. No grad student's going to do that. No team of grad students is going to do that. And just the economy of scale is going to be such that you have to rely then on the AI systems to do it for you.
Okay. So in the Q&A, not sure it's a question or just a statement, but maybe you want to comment on that. From Anno saying 300 million alerts, that's a high percentage of false alerts, it seems.
No, it's not a high percentage of false alerts. It's what you've got to remember is that there are a lot of variable stars in the galaxy, and we scan the galaxy, we don't miss it. So variable stars, variable phenomena produce alerts just as much as any supernova or tidal disruption event, or, you know, some explosive eruptive or thing. It's just a 5 sigma change in the magnitude or the position relative to the reference image. And so for something that's bright, it doesn't need to change by much to generate an alert. So if you think these are all from transients, then that's a misperception about what you're seeing in the alert stream.
Okay.
But we have a very good, again, our real bogus machine learning has a very high very low false positive rate, very high true positive rate.
Okay. The question from Simon, how difficult is it to program a TPU compared to, say, a GPU?
It's trivial. If you use Google Colab, you can actually get experience with working with a TPU. You can just select it as the hardware accelerator you want to use instead of a GPU for training. So TensorFlow and all those libraries for working with machine learning will do it for you. With using the hardware accelerator itself, the edge TPU, you just have to you have to convert your model from TensorFlow to TensorFlow Lite and then port it. But that's something that the TensorFlow libraries do for you.
Okay, many thanks. So, okay, I think we are just spot on. So many thanks, Matthew, for this great talk. And yeah, we meet again in 2030, where I hope much before, but
yes, indeed.
okay, so many thanks, Matthew.